leave a quarter on the table when you leave. Okay, online class, my apologies, or maybe you like it better this way. You're seeing a still picture of me because something has gone kaboom with the camera in the classroom, but you'll still see the slides, and you're probably tired of seeing me pace around anyway. Okay, so we've been talking about 802.11, and we've kind of come up through the development of that through 802.11n. Last time we looked at modulation and coding schemes. 802.11 is one of those things that was designed, as we've talked about, it was designed as a simple solution to a fairly simple problem. And it got applied to an entirely different set of circumstances. And so it's gotten more complex as we went along. As we've said, it was designed to solve that last few feet connection to places that it was hard to run cable. It was never designed for mobility originally. It was never designed to be a backbone connection. It's doing all of those things now. So the result is it's gotten more complex to implement. That's why you have MCS values, and in fact your last project is going to basically have you look at the effect on throughput and MCS value selection that changes in your physical layer path have to do. What we're going to talk about today is another piece of this. As we discussed early on in this module, there were originally two ways that 802.11 intended this network to work. The first one was an ad hoc. You know, this is where you need endpoint devices to be able to directly communicate. They're networks that you set up for a short time for a specific purpose. Think a bunch of people sitting around a conference table and they need to trade files. You don't have an infrastructure, the endpoints communicate directly. Still use it, still useful, it's very limited in what it can do. The other piece we talked about was this infrastructure network, and this is where we've spent most of our time. This, of course, if you'll recall, essentially is a cellular system. We have the radios that provide that last few feet connection to the user device, but to cover larger areas, we use multiple radios, and we connect those to an infrastructure network. So you have, as I show in this slide, you have an Ethernet connection with multiple access points on them, and you would place these access points to provide your coverage, the kind of thing we've been doing with our design projects. When you operate in that mode, you've essentially built a cellular radio system. Multiple physical layers so that you can cover geography. We have the ability to roam between these two as a user moves from the coverage area of the left-hand access point to the coverage area of the right-hand access point. There is a system in place that transfers responsibility between those APs for that single user. There are several protocols at work in there. Collectively, they're called the distribution system. And this works great, provided you can get cable everywhere. The problem is, as we grew into those more complex installations, and as there was a greater and greater demand for mobility, now you get to the point, like you look around now, everybody's carrying a wireless device. They expect that network to be available everywhere. And the fact of the matter is, it's just awfully hard to get infrastructure cabling everywhere. It's not impossible, but there are places where we would probably choose not to install infrastructure because of expense, where we'd like to have wireless coverage. An extreme example would be if you have two areas that you have to provide coverage on, one of them's on an island. You know, how do I do that? I can't get cable between those two, probably. So One way to accomplish this, and this happened early on, is you can replace that infrastructure cabling with another radio link. Now you have to change some things. 802.11 protocol, the timing in particular of acknowledgement packets assumes the users are very close. And so that timing is pretty tight. So as you start spanning longer and longer distances, you ultimately get to the point where the protocol won't work because it sends a packet, the radio wave doesn't have time to make the trip over, get processed, and make the trip back with the acknowledgement before the sending radio decides they didn't get it and need to retransmit. A mode called bridge mode, and we're talking about that layer 2 bridging protocol that you've all worked with in Ethernet, that sort of thing. Remember, at layer 2, bridging is how you associate two logical endpoints and exchange traffic between them. When you turn on bridge mode, one of the things you do is change that acknowledgement packet timing. And usually it's presented, in most radios, it's presented actually as a function of distance. How far apart are the endpoints? Oh, 6 miles? Okay, we'll increase the acknowledgement time to allow that to happen. The downside of this is by making that change, you make it so that user devices, endpoints, can't use that radio because it doesn't work in the standard form. So, this is a useful way to do things. This is still a regularly used solution. The advantage, I don't have to run cable. The advantage, I can configure these links individually. So I can have my user devices with that short acknowledgement timing between the access point radio, and I can have long acknowledgement timing between the link radios. The downside, if I have two APs that I need to connect this way, I've just doubled the cost of my network because I have to buy 4 radios. 2 for the bridge, 2 for the access points. You will see this used. This is commonly used as a point-to-point connection, and a lot of times what happens is you'll connect infrastructure networks with this kind of link. In fact, your project does that, although I don't make a big deal of it. That's kind of my assumption on your project. The distribution system still works. We can still roam between these two if we want to set it up that way. That's not the commonly used method on this. You know, if they're far enough apart that we're having to change that timing, probably I'm not going to roam between them, remembering that I can't associate users with the bridge radios, only with the access point radios. You okay with this? We're simply replacing a cable connection with a radio connection, but we're running the radio connection on separate radios. The major downside is expense. Okay. That was done. It is still done. It's a common tool, but there are times when it would be nice if we didn't have to use extra radios like that. And relatively early on in the development of the protocol, in fact, it's in the 1999 revision, so it's a fairly old revision. There was a description of something called a wireless distribution system, one of those clever names. That's exactly what it says it is. It replaces the cable system with the radio. The difference here is a single radio can act as both a link and an access point. That part's great. The downside, it affects my performance pretty heavily. Commonly, you see the top implementation of this, where you have an infrastructure network that connects to the internet or whatever, your wired network. You have a remote system that is, why am I worrying about this? They're not looking. A remote system that is physically far away, where I can't get cable to, and it's too far for users to be able to directly access. What I can do is put a relay radio, a repeater it's usually called, in the middle. Now what a repeater does is it will sit in the middle. It will associate with that main infrastructure radio. So it acts as a client to the AP that's connected to the infrastructure. And it receives a frame, associates with the, the BSS or the ESS, if that's what you have, receives a frame, and then something different happens. It retransmits that frame. It's a repeater. Okay? The remote is associating with that BSS, but it's getting the data from the repeater. It's too far away to get it from the access radio. Okay? Good side of this, I can extend my network. And I can do it inexpensively because I only have to use one radio to do it. Downside, what have I done to throughput? I've cut it more than in half. Remember that these are contention-based networks, so I listen to the network before I transmit. So in addition to having to transmit every frame twice, I have the time I have to listen between receiving the frame and retransmitting it. So I cut my throughput by about 60%. It's usually specified as cutting it in half, which is a lie. Almost a lie. Theoretically, if you could have instant turnaround from receive to transmit, it would cut it in half. That never happens. So you take a severe performance hit. How bad? I don't know. What's your loading? If I can support using those higher MCS values, if I can support 150 megabits throughput and my users are doing stuff that 30 megabits will support really well, then it's probably not going to be that big an issue. Latency goes up, but it's not going to hurt the ability to put data in there. Things like voice over IP, however, or two-way video, anytime you have real-time data two-way, those are going to have a problem with this because you greatly increase latency. Okay, so you got to be a little careful with this. This upper scheme, the chain, can actually be extended. I can put infrastructure radio, first relay, second relay, remote. The problem is every time I do a relay, I cut the throughput in half or more. So I start off with, I'm going to pull a number out of the air, 120 megabits. I get to that first relay. At best, I have 60 megabits on the back side of that. I get to that second relay. Now I've got half of that, at best, 30 megabits. If I have an application that's counting on 120 megabits, it ain't going to work. Okay. It's useful. Typically, you see this kind of thing for coverage for like email, short messaging, maybe some web browsing, things like that. To control that, a lot of times you'll see this set up in a star topology. And so what you'll do a variation on this. And you'll make the main radio an access point, and you'll make several remotes in a star topology. Make them be clients to that AP, and then you've only got one drop in throughput to get to where you're going. So useful tool, just go into it with your eyes open. It is a very useful thing to be able to do. Just understand what you're doing. Latency is a problem, throughput drops. Okay? Once you start doing this, you open up some other issues. Aside from the wireless stuff, when I program this, I determine how the packet routing works, because I'm going to say, here's my infrastructure AP, I'm going to put a relay that associates with that. In other words, I'm going to specify exactly how the relationships work. That's great if this stays static. Now, what happens when you have a large area to cover and you have these devices that might come and go? I'll give you an example. At big events, a lot of times you need to provide coverage for a lot of people, and I don't have time when I go in to figure out exactly how to set up all the infrastructure. How do I set up the paths? Where do I put the main AP? Where do I put all that? There's a fairly recent development. It's actually not even a standard yet. They're working on it as a standard called mesh networking. Basically what mesh networking does is uses wireless distribution system for the physical layer. Okay? So I'm going to have a wired connection to the infrastructure, and I'm going to have a lot of devices out there that are going to use WDS to move data around. So the question is, how do we do the connections? What mesh networking does is there's a protocol that decides these paths. Okay? So I don't go in and configure this. I let the protocol decide what's the optimum path between AP3 and the wired router, or AP1 and the wired router. The other place you see this is in sensor networks, where you're deploying sensors. The military does this in battlefields. Forest Service does this in very remote areas for data collection. They'll drop radios. They're not 802.11, but the same idea applies, and it's a good example. They'll drop them out there, and the radios will map the topology. Each radio maps the network from its point of view. You've seen this in router protocols. Every router draws its own map of the network. Okay? That's what's going on here. Each of these APs is mapping the network from its point of view, and it's determining the optimum way to move data to the wired network. Why would I want to do that? Okay, well, what happens if AP6 goes down? If I hard-coded the network topology, I've just killed my network. If I let mesh networking decide, that network is self-healing. And that's the big advantage of mesh networking. You can deploy it rapidly. You don't have to do a lot of infrastructure planning. The downside of it, it's very unpredictable. What's going to happen to latency? I'll choose the worst case here, AP1. What's going to happen to my latency as I remove other nodes? If I remove node 6, I've just increased the latency to get to AP1 a lot, and I've decreased throughput. So again, useful tool. Go into it with your eyes open.
Does it use the fastest path or the shortest path?
It actually uses both and weights them, and you can, in the setup of the mesh network, you can tell it whether you're more concerned about delay or about throughput. Yeah. If I'm having to move large amounts of data, but the latency doesn't really matter, I might choose a longer path with faster links. If I'm worried about latency, I might choose a shorter path, fewer nodes, running slower. Okay. Does that make sense to you? It's basically applying routing protocols like OSPF and stuff to this kind of problem, to AP problems. It's the same problem from a network topology point of view. Okay. These last two, to be honest, I'll give you John's opinion. My opinion is design the infrastructure network and implement it. Use WDS when you have no choice, or it is prohibitively expensive to use an infrastructure network or a bridge, like we've described. Use mesh networking when it meets the requirement. I've heard people talking about, oh yeah, we'll deploy this for a metropolitan network and just as nodes come and go. Okay, great. I don't want to count on it. It's not stable enough for all the applications. It's great for messaging and short, small stuff where it doesn't matter. Mesh networking is going to be interesting to follow. As of now, it is not a standard. There are several of them out there. In most cases, mesh networking is not supported by the factory software. You have to load a new firmware load. RobinNet is one you've heard of. There are probably 36 of them out there right now. When you see the standard out there, my guess is it's going to have a hard limit on the number of nodes, because that's going to be the only way they can guarantee performance. And it'll probably look a lot like your PicoNets from PANs. You know, remember, you could do a controller, some number of associate, and then you could take one of the associates, make it a bridge, so it functions as both the host and a controller. Okay? And that's all I have on that. Okay. Let me get out of this and